Yeah, I'm a genius. I don't know that. Yeah. Once the recommendation went out for like 8 weeks or whatever, I thought it was pretty clear what was gonna happen. All right, we're gonna get after it today. Got a little Desmos action. Very exciting. Wait, did I not change the stream name? I thought I did. You can mute the Twitch first so I can talk in person before I actually do math. I'm not writing anything right now. I will mute myself once the stream's like actually going. But yeah. What? Did you read the email yesterday? Yeah, you should check daily online notes in Canvas and you will already find Monday's notes exported. Yes, I will be exporting them. What? Oosh. It's also up. Oh, export that into like these, you mean import it into these notes. I don't know how to do that right now, to be honest. I'll look into it, but I mean, I'm always gonna state what the question is or what we're doing. Like, I will try never to just be like, okay, yeah, number 7, and then like not say at all what number 7 is and just be like, the answer's 6. You know, like I plan on basically stating what we're trying to do and doing it. Well, yeah, we'll spend very little time on that, and then we'll jump into 11.7, which is also posted already, I think. Should be. Yeah. Alright. Six. Alright. So how are things going? How many people have to like come back and pick up stuff to leave campus fully? Yeah, how far is that for you? Yeah, it's not bad. It's fair. I mean, I think it's like recommended, but I don't think you have to do it, right? I can't remember. I read the email yesterday, but yeah, 3 hours is much worse. I mean, I know I have some people who have to come like 9 hours, and then you have like the Texas people who are super far away. And then you have the people from the EU who attend here who can't go home. Because they literally cannot enter the EU. Yeah. All right. I'm gonna mute myself now and just talk via the stream. So there is gonna be a delay, but that way it's synced up with my writing. All right. So we're gonna go ahead and get started here. All right. I'm gonna mute you guys if you keep talking. No. All right. So, okay. I mean, I can mute if I have to, but basically the plan now, I didn't really think about this the other day, is it's probably weird to hear my voice before I am writing, so I'm going to just do it on like a 7-second delay since we have low latency. It's not ideal, but it's alright. And then for office hours, we will be able to do alright. So the plan here, yeah, for office hours, it's basically going to be the same process, except for I can go live. So if you look in the live stream thing, you have like your disconnect hang up button, the thing to the left of it, you can go live. Basically, I can share my screen and talk to you in real time using that for office hours. The difference is I can't record it, but that's fine because I don't need to record office hours. So that's the difference in terms of like why I'm doing the Twitch thing. The Twitch automatically records. But, you know, obviously feel free to unmute yourself. Chris, I'm going to unmute you now. But you should not talk unless you have a question. So, yeah, basically feel free to speak up in the live stream if you have a question. Also, you know, text either the Twitch chat or this chat, and should work out. It worked out well for the other things. Okay, so let's go ahead and get going. So looking at the class prep, yeah, the key here is to realize like what the section is and what the point is, right? So it's all about getting power series, right? This was kind of 11.6 in general. It was all about getting new power series from old power series. Okay, so essentially the fact that we know 1 over 1 minus x is x to the n from 0 to infinity, right? Just add up all the powers of x. This allows us to get things for its derivative, for its integral, for things that look like it, right? So like 1 minus negative x, you just replace the x with a negative x. And so it's all about obtaining new things from things we already know. And so this 1 over 1 minus x squared, this is exactly the derivative of 1 over 1 minus x, right? So, I mean, you can see this because 1 minus x to the minus 1, and this is actually going to be useful because we're going to do the Taylor series with this in a little bit. You take the derivative, you get negative 1 minus x to the negative 2, but then don't forget your minus in here, right? So it's also times negative 1. And so you get just 1 minus x to the minus 2, or 1 over 1 minus x squared. Okay, so because of that, well, you just take the derivative term by term, right? So 1 over 1 minus x squared should be the sum of the derivatives of all of these guys. But then that's just the power rule, right? That's super easy. We like the power rule. And so you can get at in x to the n minus 1. And notice, right, that first term is weird, so you should be careful. So maybe I'll actually just erase this. Yeah, you should be a little bit careful when you take the derivative. You're going to get that first term because of how the power rule works. When you start at 0, you'd have like a 0 over something over x to the, or just over x, and so suddenly things are a little weird, and we just kind of get rid of that and start at 1. Okay, so this is how we get our new power series, this guy right here. So if we have, why are we allowed to just drop the derivative in the sum? That's how derivatives work, right? Derivatives of sums are sums of derivatives. I mean, now it's an infinite sum, but yeah, it's the same thing. And you don't have to worry too much, right? Like, I mean, the point is it converges at least for the same things, and then the endpoints could be different, but the same radius. So that was like the theorem at the top of 11.6 worksheet. Okay, so for the next one, right, you had the natural log of 1 plus x. And, you know, this was before we had Taylor series, so I mean, you could figure out the Taylor series for this, but like, can we get it from something that we already know, is the question. And so like my first instinct then, if we're talking about derivatives and integrals, is like, well, integrating the natural log is hard. But if I take the derivative, it looks a lot like the 1 over 1 minus x, right? So I mean, its derivative is 1 over 1 plus x, which is not quite 1 over 1 minus x, but it's 1 over 1 minus negative x, right? And so we get the sum of negative x to the n, or equivalently, negative 1 to the n, x to the n. All right, I just pulled out the negative 1 to make it look more like the power series thing. So if we want to go from this was our easy one, right? But we want to end up with a series for f, not f prime. Well, then we're just going to integrate term by term, right? And so take the antiderivative term by term. And so what do we get? Well, this time it's still 0 to infinity, because we're not like multiplying by 0 suddenly, right? We actually like raise the power and we divide by something bigger. So our negative 1 at the end stays the same. It's a constant. And then we up the power by 1 and we divide by that same power. Okay? So any questions on those and what we're doing? All right. Sounds good. All right, I guess the sound of nothing. Okay, so the last problem was we want to use the fact that we know the power series for these guys, right? This is the sum of x to the n. We just did 1 over 1 plus x. This is the sum of negative 1 to the n, x to the n. And so what's the product, right? So there are a couple ways to view this. One is maybe, I don't know, I think one is hard and one is not as hard, right? You can just do these two infinite sums and do a ridiculous amount of foiling and kind of see what happens, right? So this one's alternating, but you get the same terms. And so on, and just figure out like what you get, right? So you have like your 1, you get a minus x squared, but then it's plus 2x squared because you have the 2x squareds being multiplied by 1s. And so you get, you know, definitely a 1. What about your x terms? The only x terms would be x times 1, negative x times 1. So there's no x, but we said plus 2x squared minus an x squared, so we get plus an x squared. And then for x cubed, right, you would have plus x cubed minus x cubed for the 1s, and then minus x times x squared plus x times x squared. So those cancel, so there's no x cubed term. So I'll just maybe put even like a 0x cubed. And then x to the fourth, right? We get like 2x to the fourth from doing the ones. The x cubes with the x's will cancel each other out. Or sorry, be minus 2, they'll cancel out with the x to the fourth, and then you're left with a plus x squared times x squared. So you get plus x to the fourth. And this keeps going, right? And so basically you see that the pattern is you get the even powers. For me, I mean, that's fine. You can see the pattern and realize that it's like a long process, but you can kind of see what's happening. I mean, it feels like Pascal's triangle a little bit, right? But another way, so I guess this, by the way, we could write as n equals 0 to infinity of x to the 2n. Another way to see this would be, well, 1 over 1 minus x times 1 over 1 plus x. Well, I can actually multiply these, right? I know how to multiply polynomials. And so this is just 1 over 1 minus x squared. But then just replace, right, the x to the n up here with x squared to the n, right? So this should be the sum from n equals 0 to infinity of x squared to the n. But that's the same thing, right? Because x squared to the n is x to the 2n. And so these are like two ways of getting at the same thing. And so both of them work. And so when it says like what familiar function does this result represent, I mean this is your familiar function, right? So now we want to figure out like where does this guy converge, right? Because the other ones we knew where they would converge is just the same as the thing you started with, roughly, you know, with your radius being the same if you just take a derivative or an integral. But what about multiplication, right? We don't have a theorem that says multiply things and you end up with the same radius of convergence or whatever. So we would actually have to check. And so let's go ahead and I friggin' turn my pen off. So check convergence. And so here we always want to do our ratio test, right? And so with this one we have, so it's just x to the 2n, right? So this is going to be pretty quick. So it's like the limit as n approaches infinity, x to the 2 times n plus 1 over x to the 2n. And so this is just 2n plus 2, right? And so the 2n's cancel, and you're left with just x squared. You can do the absolute value or not. X squared is always going to be non-negative because you're squaring. And so this guy is less than 1 if the absolute value of x is less than 1, right? And so this is centered at 0 because it's x to the 2n. There's no like x minus something. And so our radius here is 1. And then if you want to figure out, this says where does it converge, right? Not what is its radius. So what do we have to do to figure out exactly where it converges? What do we need? Yeah, exactly. We need to check our endpoints. Okay, and so if we plug in, right, so this one, again, it's x to the 2n. And in this case, you should realize that these are the same, right? Because negative 1 to the 2n is 1 to the 2n. They're both just always friggin' 1, right? And so the sum of infinitely many 1s, that's going to be infinity, right? And so diverges, and so our interval is exactly the open one, so negative 1 to 1. All right. Any questions before we start doing some Taylor series stuff? All right, Speaker Reese. Okay, you have a question, Max. Go ahead. Yeah, so those are the endpoints of the interval. Here, I'll explain a little more, but I'm going to okay, yeah, you muted yourself, so I can't hear my voice. Yeah, so why do we care about those, right? So ratio test, right? Ratio test says you converge if it's less than 1. Diverges if it's greater than 1. So that's why like it definitely doesn't converge outside of -1 to 1. But then if it equals 1, we don't know. And so basically checking the endpoints is exactly when the ratio test is inconclusive. Does that help? Yeah, so that's why it's always those exact points. It's exactly when the ratio test gives us 1. All right. Where are you taking these questions from? I don't see them in Discord. So, join the live stream voice chat. So you see the live stream voice channel. You should like click on the like speaker there and join, and then that should let you in. No, on Discord. He's not on Twitch? I think he is. Because he knows I'm taking questions. Yeah, there we go. Cool. Yep, so he just heard that, most likely. Yep. Okay. Yeah, it's all new for some people. It's perfectly fine. I imagine the first week is going to be a little rough. Okay, so, right, Taylor series. So this is basically like what we've been kind of working towards. So Taylor series are super important. They allow us to get power series. They give us like a specific method to get power series representations of a lot of functions, right? A very big family of functions. Basically, if you have a bunch of derivatives at a point, right? So like you can't deal with something like 1 over x, or even, sorry, like let's consider like x to the 2/3 at 0. You couldn't do a Taylor series there because it relies on having derivatives at 0. And right, like once you take one derivative, you suddenly have a 0 in the denominator for your first derivative and everything after. So no Taylor series would exist here. But if you center it literally anywhere other than 0, this derivative always makes sense. And so it's only at x equals 0, but it works everywhere else. So, you know, just center it at 1 and then look for values close to 0, and you can use like the Taylor series to estimate that. It'll take more terms to make it accurate, but eventually you'll get there, right? So it works for all others. All x not equal to 0. So we have some basic ones that you should know. Like you should memorize these, and they're the ones at the top of the 11.7 worksheet that's on Canvas, but I'm also going to just write them here. So we saw in the video that e to the x, well, we already knew a power series for it, we just didn't necessarily know like why. And so yeah, e to the x gives you 1 plus x squared over 2, and really that's the same as 2 factorial plus x cubed over 3 factorial, and so on, aka x to the n over n factorial, and that's a Taylor series. And sorry, maybe I should again put it on here since I don't know if you all have the Canvas thing open. So reminder in a little box over here, right, what is the Taylor series? So it's a specific one for f of x centered at x naught. So you would do, an times x minus x naught to the n. And then basically the key is, how do you get the coefficients, right? What are these an? So you get them from the derivative, and it's exactly the nth derivative at, you just plug in the center, and then you divide by n factorial. Okay, and so with e to the x, right, if I center it at 0, then all of its derivatives at 0 are 1. So you have numerator 1, and then 1 over n factorial times x minus 0 to the n. That's exactly how you get this, right? So here an is 1 over n factorial for e to the x at x not equals 0. Okay, so sine and cosine. Well, you did cosine for the class prep, and it looked like everyone pretty much got that. You can also view it as the derivative of sine and actually like get it that way. So once you know one, you know the other. So sine, right, is the one where you take the odd terms from the e to the x and alternate the sign. And that can be written, right, if you want odd terms, you just like, it's an even plus 1. And so we go n equals 0 to infinity. We want to switch signs, and then it's x to the 2n plus 1 over 2n plus 1 factorial. And then cosine, very similar, right? You just take the derivative, so 1 plus x squared over 2 factorial, minus. Minus plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on. And so this guy is the sum of the even powers, but also alternating. Right. So one way is to literally view it as the derivative of this, right? So you just do the derivative of each term. The other way is to look at the Taylor series, right? So like, what are the derivatives? So, we're going to center it at x naught equals 0 here. And you just start going down the line, right? So your 0th term, your 0th derivative is just your original function. So you just look at f of 0, that's cosine of 0, which is 1. F prime of 0 is negative sine of 0, which is 0. F double prime, that's negative cosine, which is negative 1. Triple prime, you get back to original sine, still 0. And then you go to the 4th derivative, and you suddenly realize you're back where you started, right? You're back to cosine. And so this is going to keep repeating. These 4, right here, these just keep repeating. And so when you look at that, that kind of tells you how to get up here, right? So you have 1, and then, so like your A0 is 1. A1 is 0. A2 is negative 1 over 2 factorial. A3 is 0. A4 is positive 1 over now 4 factorial. And you keep going down. And in general, right, so A2n plus 1 is 0. All the odd ones are 0. And the even ones are either, positive or negative. And so which ones are negative? It looks like the ones that are the halves, right? So like 2, 6, right, when n is odd. Where n is even, like 4, 8, those guys would be 1. So this is negative 1 to the n. It's negative when it's odd, and it's positive when it's even. And then over 2n factorial. Does that help? Where is the x squared coming from? You can hop in, you can say things out loud, but hold on. The x squared is coming from, these are, right, the an corresponds to x to the n. And so all I'm getting is a0, a2, a4. I'm only getting the even powers. And here I'm counting up by 1, right? N equals 0, n equals, you don't go n equals 0 to n equals 2. So that's why I'm doing like 2n, because when n equals 1, I want to jump from here to here, and then from here to here. And so I do 2n so that every time I step up by 1 with n, I step up by 2 in the power. How? Yeah. But I don't know how you're getting like x squared there, I guess. I don't know. Maybe we should talk afterwards, but like I'm not really sure how you're getting like the x squared in general there. I mean, I think you either have to do like the legitimate Taylor series. I don't see where you would get a power series in general otherwise, unless you're literally taking the derivative from sine, which is something which, again, like the sine one also comes from a Taylor series. I don't think there's like another natural way to get a power series for these guys. Okay, so I want to, and by the way, all three of these, so e to the x, sine x, and cosine of x, all converge everywhere. So not only are these like good approximations, they're not even approximations. They are literally the function for any value of x. So that's, pretty good scenario. So I wanted to go through the process for 1 over 1 minus x. So again, we know that like 1 over 1 minus x is this, right? So that is a power series. Do we know if this is the Taylor series, right? It turns out that it is, but like, let's actually construct it and see that they match, okay? Just to kind of get used to the process for Taylor series. So here, and we also already know the interval of convergence. So we've got this, and again, we're centering at 0. So that's what we're going to be plugging in. Right, and so again, I've been using n. An is going to be take the nth derivative, plug in 0, divide by n factorial. So I usually go through the third or fourth derivative. That's usually enough to figure out the pattern. If you have to go much farther, it usually gets to be a pain. So let's just write down some derivatives first. So this is 1 minus x to the minus 1. We already did this derivative earlier in class today. This is 1 over 1 minus x squared. You could also view this as 1 minus x to the minus 2. And basically what you want to pay attention to is every time the power is negative, you're going to get a negative out front. And then this is negative in here. Those negatives are going to cancel. So they're always positive. And then you keep multiplying by an increasing power, right? So this next one is 2 over 1 minus x cubed. Your third derivative is then right? This is like to the minus 3, so you bring down the 3, make it a minus 4, and so this is now 2 times 3, or 6, over 1 minus x to the 4th, and if you want one more, we can do the 4th derivative, and we would get 24 over 1 minus x to the 5th. Does anyone see, so this is 3, this is 6, this is 4, this is 24. Does anyone see what we're getting up as our numerators here? Yeah, exactly, factorials. And it's the matching factorial, right? Third derivative, 3 factorial, fourth derivative, 4 factorial. So this is n factorial over 1 minus x to the n plus 1, because the power is like 1 bigger than the thing we're getting, right? Fourth derivative, 5th power in the bottom. But we want to plug in the center, right? We have 0 here. So if we plug in 0, we get n factorial over, well, that's it. We just get n factorial, right? Because it's over 1 to the something. And, well, 1 to the anything is 1. And so this is n factorial. Well, that tells us that an is n factorial over n factorial, aka 1. Oh, but then our Taylor series, which is an times x minus 0 to the n, is exactly an is 1, x minus 0 is x, so this is just the power series we're used to for 1 over 1 minus x. Okay? Alright, and so again, that converges on negative 1 to 1. We already know that, but now we know it's also a Taylor series. So that's good practice. And so for the next part, I want to do one more Taylor series and then have you believe me that this always works out as nicely as it seems, because it does. So let's do e to the negative 2x. All right, so with this one, right, again, that's our f of x, centered at 0, which again, we like to center things at 0. It won't always be the case, because sometimes 0 will like go in a denominator, or like ln of 0 could happen, then we'd have to dodge 0 for it to make sense, but a lot of times that's very convenient for us. So f of x is this, so f prime of x is negative 2 times e to the negative 2x, chain rule. F double prime, well, we get 4 e to the minus 2x, right? We multiply by negative 2 again. F triple prime, negative 8. Does anyone have an idea of what the nth derivative is then? It's close. Close. I don't think we were getting... Yeah. Okay. So negative 1 to the n times 2 to the n e to the minus 2x. Or if you want negative 2 to the n. Yeah. Either one of those. They're the same thing. But... yes, this is what we would get, and so if we want to do the nth derivative at 0, well, that just gives us negative 2 to the n, because e to the 0 is 1. So our series then is this guy. So we have negative 2 to the n over n factorial times x to the n. All right. Now I want to compare this to e to the x. Right? E to the x is x to the n over n factorial. Do you see how close they are? Right? This guy has this -2 here, and so we get the extra -2 to the n. Well, think about what we've done so far, right? Like with 1 over 1 minus x, and we wanted to figure out 1 over 1 plus x. We rewrote it as 1 over 1 minus -x, and then substituted in. Well, this is the same thing here, right? So like e to the -2x should be, let's just do -2x to the nth power over n factorial. Well, then you just separate them, and that's exactly what we have up there, right? You can just separate these and get what we had. So basically what the point is here is that substituting still gives us a Taylor series. Okay, and so basically we can use the same techniques that we've already developed of substitute in when you see something that looks exactly like it, and that's still going to be a Taylor series. And so same, by the way, with derivatives / integrals. So not only do they give us new power series, those actually remain Taylor series. Okay, so that's super useful. It's also good to know some terminology here. So I've said Taylor series for all this stuff. You will also see Maclaurin series. So maybe I'll put like a little definition here. Maclaurin series, named after Colin Maclaurin, who's a mathematician, is a Taylor series centered at 0. So a lot of the time, right, we are dealing with things centered at 0, so that you'll often see, like, find the Maclaurin series. What does that mean? That just means find the Taylor series centered at 0. And there's a nice little, like, math history story there, but I'm not going to get into it right now. Yeah. Okay. So if we want to find the Maclaurin series, I know I said Taylor centered at 0 up there, but let's call it this Maclaurin series for, say, 10 cosine of root x. Well, we can substitute, right? So we know cosine. So this should be your process here, right? It's like, okay, what is this roughly? Like, if I know cosine, then I can substitute in the root x for x, and at the very end, I can multiply by 10. And so basically, the fact that I know one of these basic ones, so like those 4 at the top of the page for 11.7, like those are the ones you're going to use over and over again. And basically be flexible with those to get a bunch of new ones. So cosine of x is -1 to the n, x to the 2n over 2n factorial. So then 10 cosine of root x is just multiply by 10, -1 to the n. Now instead of x, it's root x to the 2n over 2n factorial. And then this can be simplified, right? Because root x to the 2n is, well, you just square it and then raise it to the n. So this is x to the n, right? And so here I'll actually put on these x to the n over 2n factorial. And so this would be your final answer. And this is a Taylor series because Taylor series behave nicely with substitution. Okay, so I want you guys, you can talk together in this live stream chat and figure out, and like if some of you want to like break into the working together or something, feel free. Talk about 2 and 3 and see if you can figure out, or I guess 2, 3, and 4. I think we should be able to get those within a couple minutes based off of substituting from things we already know. I mean, you can either text, but I recommend unmuting yourselves, and then I won't talk so that there's no feedback. Oh, they're in the. Oops. Okay, cool. Yeah, sorry, I muted myself on stream so I could talk to you in real time, but now I'm back and muted in stream. Or sorry, muted on Discord. Yeah, so the point is that like these are the pieces, and I guess this in general looks like 1 over 1 minus x, right? You just kind of identify those first, and then just start by writing out what that is, right? So e to the x is this guy. So x squared times it is going to be just x squared times every term. You can just distribute that in. I'll leave it outside for a second and then distribute it in. Right, so like just distribute. Well, what happens when you multiply x squared times x to the n? You get x to the n plus 2, right? And so that means this guy will be the sum of x to the n plus 2 over n factorial. Does that make sense? Cool. Okay, so for this next one, right, so you just start by sine x. Now here, I'm noticing I'm subtracting some stuff. And let's actually write out what sine is this way. Oh, I think that was supposed to be a 3 factorial. It's fine. That's a typo from me. I wanted that to actually cancel. This is supposed to be a 3 factorial, sorry. And then this guy, right, you just keep going, blah, blah, blah. And again, another way to write it is like the sigma notation, but I think here it's maybe less clear at the start. And when I subtract, right, these two guys will cancel, right? So like this goes away and this goes away. And so the sine x minus x plus x cubed over 3 factorial is you start at x to the 5th and then keep going. And you still alternate and everything, but you go there. And so on. How could I change? So my question for you now is, if you look at the sigma notation, what changes from this if I want to rewrite this one? Can you figure out what's different? Or how I can rewrite it? Yeah, exactly. Where does it start now? See Adam typing. Yeah. Yep. Right, so when n equals 2, 2n plus 1 is 5. And then n equals 3, it's 7, and so on. And so basically, this gets you exactly what you need. And another way to think about that, right, n equals 0 and n equals 1 were your first two terms. Those are the guys that we canceled away. And so those guys are gone. Okay. All right. And for this one, this is one we've already done before, right? So I mean, this we know is -1 to the n, x to the n. We've done this several times. You just rewrite it as 1 over 1 minus -x. And replace. Okay. And I want to finish with looking at 5 and 6 because they're actually super fast. So if you look at this guy, so just to keep track down here, this is what we have going on. So does anyone see what the pattern is? So I mean, the bottom seems kind of obvious, right? It's like something over n factorial. What is it over n factorial? What's our numerator? to the n. Yeah. Yep. And so the question is, like, how do I know what this converges to? So before, right, we couldn't do it because, like, this isn't geometric and it's not telescoping. But now we know, because we know that e to the x is, so this is the sum, e to the x is the sum of x to the n over n factorial. Well, all I've done is I've taken this thing and I've replaced my x with 2. So this is e squared. So I can take this sum, recognize it as the Taylor series with a specific x value, and then just plug it in. Does that make sense? I mean, I'm just recognizing that, like, something to the n over n factorial is exactly what e is, and here I have 2 to the n, and so I've just made x equals 2. So it's just like a direct substitution for a specific x value. And so the last one that I want to talk about very briefly here, and hopefully this will make that a little more clear, or at least get us used to the idea. If you see this, right, this equation looks tough initially, right? Like, you can't solve for x very easily. But what is the left side? Right, that it's a trig function. Wrong trig function. But yeah, this is sine. Yeah. And so this is the same thing as saying sine of x equals 1. And we know when that happens, right? So x is arcsine of 1, which is pi over 2. Right? And I mean, if you want it to be a function, right, then it's pi over 2. And so basically, yeah, it's recognizing these infinite series as specific examples of these functions. And so you can solve for this. So, like, right, if you just saw pi over 2 minus pi over 2 cubed over 3 factorial plus pi over 2 to the 5th over 5 factorial equals 1, you'd be like, what the heck? Like, I don't know how to do that. But then when you realize this is just sine of pi over 2, well, then that's really obvious, right? So yeah, it's recognizing these main ones. So, like, really hammer home those 4 guys at the top of the 11.7 worksheet. E to the x, sine, cosine, and 1 over 1 minus x. All right. So I'll be around for a bit here. I have a meeting at 3:15 that's really important, and I have to go on a Zoom call for that. But later today, I will announce new office hours. I'm going to do the class-specific ones, and that way I can do the go live that Reese was doing in the office channel there, so I can share screen with you and talk to you in real time. And I think that'll be a good way to do office hours. All right, so yeah, I will go ahead and in stream, and then I'll be in the office if you want to talk for a bit.